in 1.3, we're going to still talk about limits, so more about limits. And then we're going to talk about infinite limits and limits at infinity. When we talk about infinite limits, we're dealing with vertical asymptotes. So this is something you did in Math 3. We've talked a little bit about it in previous lessons. We're going to kind of tie that all together here. So up here we have a function f of x equals, and we have x minus 1 over x minus 1 times x minus 2 squared times x minus 4 squared. It says that it has a hole at x equals. So remember what we talked about. If you have a factor that reduces, like those x minus 1s do, that means at this discontinuity, when x is 1, there's going to be a hole in the graph. So we have a hole when x equals 1. Then it says an even vertical asymptote at x equals and an odd vertical asymptote at x equals. The way you tell that is you look at their powers. So right here, our other time x, we have a discontinuity as x equals 2 and at x equals 4. Because this one has a power of 2, we call that an even asymptote. So we're going to put at x equals 2, there's an even asymptote. This one has a power of 3, so at x equals 4, it has an odd asymptote. So since in the graphs below, the vertical asymptotes are labeled even or odd. So if it's an even asymptote, this is what it ends up looking like. So if you look at the vertical asymptote, either they both go up to infinity, like that one does, or they both go down to negative infinity. Again, that's if it's even. So for example, when x equals 2, on that function up above, that's what would happen. If it's an odd asymptote, then they go opposite directions. So one goes down, and then one goes up, going that direction. Or you could say, right, this one, from the left, it goes to infinity. From the right, getting closer, it goes to negative infinity. So it's really helpful for us to know even or odd asymptotes. And the part of the reason why is, before when we said, when there's a vertical asymptote, we always said that the limit doesn't exist. But we also said you could be more specific, and you could say it goes to infinity or negative infinity, right? So it says up here, right, you've seen examples where the limit doesn't exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is even. And the reason why we can do it when it's even is because they're both going the same way. Either they're both going up to infinity, or they're both going down to negative infinity, both sides. Or if it is an odd asymptote, then we can say that if it's a one-sided limit, then we can say that it also goes to infinity or to negative infinity. But just remember, side note, this still means on both those cases, it still means the limit does not exist. You're just being more specific and saying which direction it's going. Okay, so look at this first example. I have the limit as x approaches 2 from the positive side of x plus 2 over x minus 2. Hey, by the way, this is an odd asymptote, right? It's to the first power. That means they're going opposite direction. So if we were coming from both sides, we could not say infinity or negative infinity, but this one's a one-sided limit. Okay, so the way you're going to do this is just to test points. So I'm approaching 2 from the positive side, so pick something to the right of 2 and see what happens. And we don't have to actually calculate it. We just need to figure out if it's positive or negative. So let's say we pick, for example, 2.1. The top would be positive and the bottom would be positive. What that means is that it goes to infinity, positive infinity. Okay, as I'm approaching from the left side, again, pick something close to 2 from the left side. So if I plugged in, for example, 1.9, I get a positive on top, 1.9 plus 3. On the bottom, I get 1.9 minus 2. That comes out to be a negative. A positive divided by a negative is a negative, so that one goes to negative infinity. So you can see it was an odd asymptote, right? So as I approach from the right side, it's going up. As I approach from the left side, it's going down. Okay, look at 3. Hey, this one is even. That means both sides are going to go the same direction. It says we're approaching 1 from the positive side. So again, let's just pick a number to the right of 1. We could plug in, for example, 1.1. I would get a negative on top, all right, 1.1 minus 2. The bottom is always going to be positive, right? If I plug in 1.1 minus 1 and then I square it, it's going to come out to be a positive. A negative divided by a positive is a negative, so it goes to negative infinity. Hey, number 4, automatically, we should know that it's got to go to negative infinity too because it was even, right? It's the same function. But let's just double check. If I picked, for example, 0.9, well, 0.9 minus 2 is a negative. 0.9 minus 1 is a negative, but then we're going to square it, which is going to make it a positive. It should go the same direction. In that case, they're both going down. Okay, number 5, x squared minus 4 over x minus 2. Make sure that you're careful and we don't automatically assume that it's going to have, just because we get a 0 on the bottom, that we're going to get a vertical asymptote, right? If I plug 2 in, I get 0 on top and 0 on the bottom. Remember, that's an indicator that this is not a vertical asymptote, this is a hole. And let's just double check, let's see if we can simplify it. Have the limit as x approaches 2 of, I've got x minus 2 times x plus 2 all over x minus 2. Okay, well those reduce out. Now try plugging 2 in again and we get 4. So just be careful. Again, if you get 0 over 0, it's not a vertical asymptote, more than likely anyway. It's usually going to be a hole in the graph. Okay, so limits at infinity. This is a little bit different. So those were limits that went to infinity. These are limits at infinity. So it says if the graph of a function approaches a horizontal asymptote to the left and or to the right, it is said to have a limit at infinity. If the asymptote is y equals L, so let's say y equals 3 or y equals 0, then the limit as x approaches infinity of f of x is L. It's whatever it approaches. In other words, limits at infinity give us end behaviors of the graph. That's really important. You got to connect these. Whenever you're given a limit at infinity, as x approaches infinity or negative infinity, what it's really asking for is the end behavior. For large values of x, the highest degree term in the numerator and the denominator dominate the other terms and are the only terms you have to consider. I'll show you an example of that in just right now. So let's look at number 6. So it says find the horizontal asymptotes. Okay, so when we go to look at f of x, we want to find out as I go to the right, does x approach a number, does y approach a number, excuse me, or as x gets really small to the left, does the y coordinate approach a number. So when we go to do this, like it was just saying, we only look at the term with the highest power. So we don't even care about the 3x squared plus 2. All I care about on top is the 5x to the 4th because it has the highest power. On the bottom, all I care about is 10x to the 4th because it has the highest power. And there's 3 things that could happen. Let's write down all 3. The first one is, I will use that first case that I have up there, right, where the 2 are equal to each other. So if that happens, then if I have ax to the n, you know, we don't really care what comes after that, over bx to the n. Again, we don't really care about that. But if they're tied, if they have the same thing, then your horizontal asymptote will be y equals a over b. We just take those coefficients out in front. Right? The x to the n, you kind of think of them that they cancel each other out, and it just equals a over b. That's what we have here. This is case number 1. Right, I've got an x to the 4th and an x to the 4th. So all I do is take 5 over 10. So we'd say there's a horizontal asymptote at 5 over 10, which is a half. Okay, you look at number 7. So again, this is the second case. If I compare those, I have 5x to the 4th. I only care about those ones with the highest power right there. If the power on the bottom is bigger than the power on top, so let's write that down. This is kind of out of order. I'm going to come over here. This is number 2. Okay, so if I have ax to the n over bx to the m, you know, it doesn't really matter what comes after that. If m is greater, oops, sorry about that. If m is greater than n, then the horizontal asymptote is at y equals 0. What essentially happens here, if you think about it, is this one, the bottom one's going to get bigger faster than the top one. So if the bottom gets bigger faster than the top, what happens is your number gets closer and closer to 0 because you're dividing a smaller number by a bigger number. So this one would just be y equals 0. That's case number 3, or 2, excuse me. Okay, case number 3 is like this one, and that is like, look at your highest powers. So there and there. The highest power on that one is on top, so that's case number 3. Let's write that one down. So case number 3, whoops, sorry about that. So case number 3 is when you have that ax to the n over bx to the m, right? We don't care about what comes after those highest powers. And if the top n power is greater than the bottom one, m, then this is what happens. It's going to be there is no horizontal asymptote. What that means is your graph's either going to be going up to the right or down to the left, but it's not going to approach a number. So those are your 3 cases. If I come back up here then, if you look at it, that one is bigger than that one. That means it does not exist. We can be more specific here, though. We just talked about how we could say it's either going to be going up and down. So we could figure out if it's going to infinity or negative infinity if we wanted to. So let's think if I plug it in really big numbers. Again, it doesn't really matter what follows the 5x to the 4th and the 10x cubed because those higher powers are going to kind of take over. So all I'm going to think about, so if I plug in numbers to the right, am I going to get a positive or a negative? So if I plug in really big numbers on top, that's definitely going to be a positive, right? Because you're taking that number to the 4th power times 5. On the bottom, I got 10 times, again, a positive number. So if you want to be more specific, we could say as x goes to the infinity, it's also going to go to infinity. So there isn't a horizontal asymptote, but it does go to infinity. Whoops, I wrote that in the wrong spot, didn't I? Let's go back up here. Sorry. Plus goes to infinity. Okay, the next 3 problems, notice they're exactly the same functions. The only difference is instead of writing it as, asking you to find the end behavior, it's writing it as limits. It's exactly the same thing. So if you look at number 9, it says the limit as x goes to infinity. All that means right there is as I go to the right, does the function approach a number? In other words, does it have a horizontal asymptote? So limits at infinity are exactly the same as end behavior. It's just what we found up above. So we know here, right, this is the same problem we had up here. We know that the y value is going to get closer to a half as I go to the right. As I go to the left on this one, right, the bottom's bigger than the top. That means it gets closer to 0. This one, the top's bigger than the bottom. That means that there is no horizontal asymptote. But we just said you're going to get bigger and bigger numbers back out, so it's going to go to infinity. This is really important if you look at this number 12. When we go to compare this, a lot of times we end up comparing like the squares up here. You shouldn't do that. Right, it says up here, make sure you consider the highest degree terms, not the highest degree factors. What we need to do is figure out what would the first term be if we were to multiply both the top and the bottom out. You don't have to multiply the whole thing out. That would be really long. Right, I'd have to go x minus 1 squared and multiply that out, and then take my answer and times it by 2x plus 3, which we could do, but it would take a while. Instead, all I have to think about is if I were to multiply it out, what would be my highest term? So what would end up happening, right? If I multiplied out x minus 1 squared, the highest power in there would be an x squared. There'd also be like, what, x squared minus 2x plus 1, but we don't care about that. Over here, my highest power is a 2x. If I multiply those two together, I would end up with a 2x cubed. Now again, there'd be a bunch of stuff that comes after that, but we're not going to worry about that. We'd only care about that highest power. Do the same thing on the bottom. Be really careful with this one. This one has a 3x. If I were to multiply that out, it'd be 3x squared, as in 3x squared. So don't just square the x, but square the 3. So that would be 9x squared. Times it by that x. The highest power on the bottom would be 9x to the 3rd. And again, there'd be a bunch of stuff that followed that. Okay, now I'm comparing them. Hey, they've got the same power, x cubed and x cubed. So I just take the numbers in front. So the answer is going to be 2/9 on there. So if it isn't multiplied out, you have to figure out what that first term would be if you were to multiply it out. So it's 2 over 2/9 is what it's going to get closer to. So that's just a quick side note. Be really careful with that. You're comparing the highest terms, not the highest factors. Okay, these are a little bit tricky. So if you have a rational function, and all these previous examples we did are rationals, that's when you just have a polynomial on top and a polynomial on the bottom. When that happens, they will have at most one asymptote. They won't. But if you have a radical function, a lot of times you'll have two asymptotes. So look at these examples 13 and 14. So it says, what's the limit as x approaches infinity of the square root of 4x squared minus 3 over x? First thing that's kind of tricky is when you go to compare these, I don't compare 4x squared to x because it's the square root of 4x squared to x. So I have to figure out what would my highest degree be, but to do that I have to take the square root of 4x squared. So the square root of 4x squared is 2x. Okay, now compare the top and the bottom. I've got 2x to x. They're both degree 1. Well, that means they're tied, so I take the numbers in front, so it's going to be 2 over 1. Now here's the tricky part, is it could be plus or minus 2 over 1, or plus or minus 2. You can't tell which it's going to be just by looking at it, so all we're going to do is plug in numbers to see what happens. So I'm thinking about this for a second. I want to find out as x goes to infinity. That means x values are getting really big. Well, if they're getting really big, this top part, if I plug in a really big number for x, I square it and times it by 4 and minus 3, I'm going to get a positive on top. It doesn't want to write that. I'm going to get a positive on top. On the bottom, if I plug in really big numbers for x, like 100, 1,000, 10,000, I'm going to get really big positive numbers. So I get a positive over a positive. What that means is it has a limit of a positive 2. But I couldn't tell that just by looking at it. I actually had to plug in numbers and see what happened. So over here we have the exact same problem, right? So same thing, it's 2x on top, right? Square root of 4x squared, x on the bottom, they're tied. But I always got to think it could be a plus or a minus. Now I'm going to plug in really big numbers going to the left. So pick some really big numbers going to the left. You could do, a negative 100. On top, right, negative 100, when I square it, I get a positive. Times 4 is a positive. It's going to be a positive on top. On the bottom, if I plug in a negative 100, that's going to be a negative. A positive divided by a negative, so that means it gets closer to negative 2. So this one has two different asymptotes. As I go to the right, it gets closer to 2. As I go to the left, it gets closer to negative 2. This will never happen with rational functions. The two cases you'll see it most with is with radicals like this one. The other one was with absolute values. So if you have a problem that has an absolute value on the top or bottom, you have to do the same thing. You just have to plug in numbers to find out as I go to the right will be the positive or the negative. You do the same thing as you go to the left. Hey, this last thing, you just talked about some different end behaviors. So let's talk about e to the x. Just remember really quick what the graph of e to the x looks like, right? It comes in along the x-axis, crosses a 0, 1, and is going up. So as x goes to negative infinity, that means as I go to the left, right? So as I trace along to the left, there's a horizontal asymptote. It gets closer to 0. As x goes to positive infinity, as I go to the right, there is no asymptote, right? It just keeps going up. So it goes to infinity. So we can use that to look at this next problem. It says, what is the limit as x approaches infinity of e to the negative x plus 2x squared minus x over x squared plus 3? So if you have a plus or a minus, we can really do each of these separate. So I'm going to start, what is the limit as x approaches infinity of e to the negative x? So think about what the graph of e to the negative x looks like for a second, right? And negative is with the x, so it flips it horizontally about the y-axis. So instead of coming up the way we did over there, it's going to be flipped across. It's going to come down this direction. So think about what happens to this as I go to infinity. So if I'm tracing along here, as I go to infinity, this graph is getting closer to 0. So that part's going to be 0 plus. And now just do the top part. Now remember, we only compared the degree of the highest power. So I'm going to compare that one to that one. They're tied. They're both degree 2. So I take the numbers out in front. So it'd be 2 over 1. Well, 0 plus 2 is 2. All right, look at 18. I have 2x squared plus 4x over e to the x plus 3x squared. Now we said we always compare the highest powers. Hopefully this makes sense. You guys talked about this in Math 2 and Math 3. But e to the x gets bigger faster than 3x squared. Exponentials get bigger faster than polynomials. So what that means is I'm going to compare what happens. I'm going to compare the 2x squared up on top to the e to the x on the bottom. And I'm just thinking, what happens as x gets really big? Well, as x gets really big, this one goes to infinity, and that one goes to infinity. This is a tricky part, though. The bottom one, e to the x, gets bigger faster. So it gets bigger faster. So that means as x gets bigger and bigger, the bottom's going to get bigger faster than the top, which means you're going to get closer and closer to 0. It's really similar than if I had 2x cubed, 2x squared over x cubed, right? This is going to get bigger faster than that is, which means it's going to go to 0. Same thing happens here. E to the x gets bigger faster than 2x squared, so it's going to go to 0. Hopefully we can make some connections here between what you've already done with end behavior, like you did last year. We need to connect that with what you're doing this year with limits, because it's really the same thing. Whenever it says the limit as x goes to infinity, or the limit as x goes to negative infinity, just think end behavior. Like, what's happening to my graph as x gets really big or as x gets really small? And hopefully we make those connections. We can use that prior knowledge and make it a little bit easier for us. All right, thanks, guys.